Hello, welcome to the wonderful world of physics. This is the homework solutions video for Chapter 4 of Physics 102A, Force and Newton's Laws of Motion. And there in the picture you see an excellent example of Newton's third law of motion. In order to launch the space shuttle upward, it shoots the thrust downward. And Newton's third law says for the force of the shuttle shooting the thrust downward, the thrust shoots the shuttle upward. Let's begin with problem number 33. It says at time 0, a 0.230 kilogram air track glider is moving rightward at 2 meters per second. At time 4 seconds, it's going leftward at 1.2 meters per second. Determine the magnitude and direction of the constant force that acted on the glider during this interval. All right, so let's list out the relevant information. We have an initial speed, plus 2.0 meters per second. Final speed, it's going in the opposite direction, so we'll say velocity 1 is negative 1.2 meters per second. We've got the mass, and we see a time interval of 4 seconds. The question is asking about the force that caused this, and we're going to invoke Newton's second law, F equals ma. And so let's figure out what the acceleration is. So acceleration is change in velocity over the time interval. We'll do final minus initial, negative 1.2 minus 2 meters per second, and that gives divide by a time of 4 seconds, and that gives acceleration of negative 0.8 meters per second squared. Now, the negative just has to do with how we set up our different directions. Initially, in calling V naught positive 2 meters per second, that means it was going in the positive direction, and I'll call that to the right. And then finally, it was going negative 1.2 meters per second, which would be to the left. So the acceleration is to the left, negative 0.8 meters per second squared. Then we find the force, its mass times that acceleration, and we get, when we multiply those, it comes out to be negative 0.184 newtons. However, usually, unless we want to express it as a vector, we give it as a magnitude. And the book actually says determine the magnitude and direction of the constant force. So the magnitude is the positive value, 0.184 newtons, and it's going to the left. Number 35, find the magnitude and direction of the force needed to accelerate a 100-gram mass with the acceleration that is given. And so here I have the force equals mass times acceleration. I've done it in my stacked vector notation. It's good to draw a picture. So as I've drawn a picture, that's with the green vector right here, negative 0.255, positive 0.650, so it's a second quadrant vector. And if that's the acceleration, that's also what the force is going to be in that second quadrant. So we multiply mass, we get the force, and we can find the magnitude by using Pythagorean theorem. There it is, 0.0698 newtons. We want to find the direction, and so theta is the arctangent of the y component of force over the x component of force. When we take that arctan, we get negative 68.6 degrees. Now let's go look at the picture at what negative 68.6 degrees looks like. It's here in the fourth quadrant. It's going in exactly the opposite direction. And that reminds us that when we have a second or third quadrant vector and we're taking the arctangent, the calculator will only give us a fourth or first quadrant answer. So we have to add 180 degrees to get it in the correct direction. So we'll take that negative 68.6, we're going to add 180 and get 111.4 degrees. And really with proper significant figures, we're only allowed 3 significant figures. So let's call that 111 degrees. Number 39. Find the upward acceleration of Earth due to a 1,000-kilogram object in free fall above the Earth. Hint, use Newton's third law. So it seems kind of weird that something falling towards the Earth, even a pen that's falling to the ground, causes a negligible yet a non-zero acceleration upward of the Earth. This is Newton's third law, the idea that the force of, I'm going to call the object A. The force that A pulls on the Earth is equal in magnitude to the force that the Earth pulls on A. And there I've drawn a little picture there, which means that magnitude of Earth, mass of Earth times acceleration of Earth equals mass of A times acceleration of A. We want to solve this for acceleration of Earth, so there we go. It's going to be the ratio of the masses times the acceleration of A. So the ratio of the masses, we have mass of A over mass of E. The acceleration of the falling object is g, 9.80 meters per second squared, which you learned back in chapter 2. And so we'll plug in all the values. It's going to be a very small acceleration because of the ratio of those masses. And we get 1.64 times 10 to the negative 21 meters per second squared. That's the acceleration of the Earth upward. Number 45. A net force of 150 newtons acts on a 5 kilogram block initially at rest. Find the block's speed after 2.5 seconds. Well, we're going to get speed using kinematic equations, but first we need acceleration. So we'll use Newton's second law. Acceleration is force divided by mass. So 150 newtons over 5 kilograms, it's an acceleration of 30 meters per second squared. And then we'll plug that into the kinematic equation, V equals V naught, which is 0 plus AT, and we get 75 meters per second. Number 47. A constant force of 35.2 newtons I hat changes a ball's velocity from negative 3.25 meters per second I hat to 4.56 meters per second I hat in 3.5 seconds. Find the ball's mass. So I start this problem, as always, by listing out the given information. And we want to know the ball's mass, so we're going to think about F equals ma, and we're going to be solving for that mass. So force equals mass times acceleration. Now we're not directly given acceleration, but we are given velocity, the change in velocity and the time increment. So I'm going to replace acceleration in the x direction with change in velocity over time. And now I'll plug in, we could be solving directly for mass, but here I've chosen to plug in all the numbers. 35.2 newtons for force is the mass times final minus initial. Make sure you keep your positives and negatives straight. So final is a positive velocity, initial is a negative velocity. Divide by the time and you get 15.77 kilograms. Number 49. Two forces act on a 24 kilogram cart, resulting in the given acceleration. One force is 32 I hat minus 48 j hat newtons. Find the second force. Let's go down to the bottom of the page. I've drawn a picture. My blue vector at the bottom shows the first force. 32 in the x direction, negative 48. That's the way it's pushing. What I've drawn in the red vector is the acceleration, negative 5.17 and up 2.5. And don't pay attention to the scales, the relative lengths of those, because they're not the same dimensions anyway. One is newtons, the other is meters per second squared. But pay attention to the angles that they're facing. The first force is pointing in this blue direction, down and to the right. And yet overall, the object is going to be moving up and to the left. And so that tells me conceptually that there's going to be an even bigger force. That second force is going to be much bigger. It's got to be pushing to the left and overwhelming the rightward force of the given force. Also, it's got to be pushing up enough to counter the downwardness of the given force. So conceptually, we can see it's going to be a large force to the left and upward as well. Well, let's actually go through the math and see what we get, see if we get that result. We'll use F equals ma. Here I've used the beautiful stacked vector notation where the x components are on the top, the y components are on the bottom. So we see in the x direction, 32 newtons plus F sub x, this is right here is our mystery force, equals mass times acceleration, 24 grams times negative 5.17. And in the y direction, negative 48 newtons plus the y component of the mystery force equals 24 kilograms times 2.5 meters per second squared. So when I break those down into two separate scalar equations, this top equation here is the x component. The bottom equation is the y component. When we solve those equations individually, this top equation gives you that the x component of F is negative 156.1 newtons. When we solve the bottom equation for the y component, we get F sub y is 108 newtons. So here we've solved through these two scalar equations. We've solved for the x component and the y component. And now let's give the answer in appropriate I hat, j hat notation. So we get negative 156 newtons plus 108 newtons j hat. Now, actually, we're only allowed to give two significant figures, and so we could abbreviate that as, for two significant figures, negative 160 in the I hat direction and 110 in the j hat direction. Number 51, an Olympic bobsled starts from rest and slides down a frictionless 7.5 degree slope. What's the final speed after 25 seconds? All right, rather than re-deriving this every time, I want you to remember, it'd be useful to remember that when something is sliding up or down a slope, there are these equations that I derived in class, and it's just a whole lot easier if you remember those equations. However, let me re-derive it quickly for you, and then we'll get down to the equation. Here we have the setup. We're going to rotate, so our x-coordinate goes parallel. It goes downhill and parallel to the ramp. The y-coordinate is up and perpendicular to the ramp. We'll use F equals ma both in the x and y direction. So in the x direction, the sum of the forces in the x direction equals mass times acceleration in the x direction. There is only one force. If you look at those green vectors, there's only one force that has an x component, and that's mg sine theta, the x component of gravity. So mg sine theta equals mass times acceleration. All of the acceleration is the x component of acceleration. That's why I dropped that x subscript. And we get acceleration as g sine theta. And this is the equation that I've told you it's useful just to remember that. Acceleration is g sine theta. When we plug in the values that are given in the problem, it says it's a 7.5 degree slope. Then we get times sine of 7.5 degrees, we get acceleration is 1.27916 meters per second squared. Now, by the way, I've also over here, it's not going to be relevant to solving this problem, but you should remember that any vector equation is a bunch of scalars rolled into one. And so let's do F equals ma in the y direction. And again, you've seen this in class, but just to see where it takes us. In the y direction, there's the normal force in the positive direction minus mg cosine theta, so gravity in the negative direction. So we have n minus mg cosine theta equals, there's no acceleration in the y direction, so we say 0. And we get that the normal force is mg cosine theta. That doesn't help us in any way to solve this problem. However, if the problem had involved a slope with friction, then friction is related to normal force, so we would need that. But we'll just put that off to the side and think about it for another problem. Let's go back here. Back on track, the acceleration, we've got it. And the problem says, what is its final speed? It starts at rest. How fast is it going at 25 seconds later? So v equals v naught plus at. V naught is 0. We plug in those values, and we get 32 meters per second. Number 59. Similar situation. Olympic skeleton sled racers can reach speeds of 40 meters per second. Find the slope needed to reach that speed after a 30-second run neglecting friction. All right, this is like the previous problem, but we are now solving for the slope. We are given information that'll get us to acceleration, then we'll solve for slope. We remember from the previous problem that acceleration is g sine theta, so sine theta is going to be acceleration divided by g. All we have to do now is figure out what acceleration is. So let's think about the kinematics. It says a time of 30 seconds, starting at rest, so v naught is 0. Final v is 40 meters per second. So we're going to solve for acceleration. Acceleration is v minus v naught over t. 40 meters per second, we could say minus 0 over 30 seconds. And that gives an acceleration of 1.3 repeating meters per second squared. We're going to now plug that into the sine equation. So sine theta is a over g. And we'll do 1.3 repeating divided by 9.80. We're going to take the arc sine of that, and we get 7.8 degrees. Number 69 says, a steel cable lifts a 350 kilogram concrete block vertically. The maximum safe cable tension is 4,200 newtons. What is the maximum upward acceleration of the block? All right, let's draw a force diagram. And we're going to think about the object of this force diagram being the load that is being lifted, the concrete block. Let's think about what forces are acting on it. We've got tension that is going up. We've got gravity pulling down. So T upward, mg downward. We'll do F equals ma. We only have to invoke the y direction. So the upward force tension minus the downward force mg equals ma. And we're going to solve for acceleration. And so in solving for acceleration, we just divide both sides of the equation by m. So now we get acceleration is 4,200 newtons, which is the maximum tension, minus mass times g divided by the mass, and we get 2.2 meters per second squared. So given the maximum tension, this is the maximum acceleration. Number 75 deals with something on an incline, but now there's friction. It says a wooden block slides down a 28-degree incline with acceleration 3.85 meters per second squared. Make a force diagram for the block. Find the coefficient of kinetic friction. All right, there's your force diagram, what we've seen several times before of an object on a slope. We have normal force going in the positive y direction. Gravity goes in the x direction for mg sine theta, in the negative y direction for mg cosine theta, and we have friction. Now we have to make a choice. What direction does friction go? And since the wooden block is sliding down the incline, remember friction always goes against motion. So if the block is sliding down, friction is going up the incline. So that'll be in the negative x direction. Let's do our F equals MAs, both in the y direction, x direction. And in the y direction, this is, I derived this not only in class, but previously I showed this in, I think it was problem number 51, that we get the result that normal force is mg cosine theta. And this is nothing specific to this problem. That's just when you have something sitting on an incline, the way we set it up. In the x direction, I derived this in class, but here I'll go through it again. The forces in the x direction equals mass times acceleration in the x direction. So we look at the force diagram. Mg sine theta is positive, minus friction equals ma. And then we're going to expand that friction. Remember that friction is mu sub k, the coefficient of friction, times normal force. And here I've just included them all in this one term. Mu sub k times mg cosine theta, which we got up here. So we have now mg sine theta minus mu sub k mg cosine theta equals ma. We can divide out the mass because it's a factor in every term. We can factor out g, and we're left with right here this equation in this box that I highly recommend you just learn. rather than having to go through this derivation whenever you come across an incline problem, it's so much easier just to remember that without friction, A is g sine theta. With friction, it's g times sine theta minus mu sub k cosine theta. All right, now from here, we recognize we have to solve for mu sub k, so we're going to go through the algebra step by step, peeling away things from mu sub k. So the first thing we do is recognize that the quantity in parentheses is being multiplied by g. So I'll get rid of that by dividing both sides of the equation by g. The next thing I see, if I just focus on what's left, I want to get rid of that sine theta that's being added. So I'll subtract sine theta from both sides. Now I've got a negative mu sub k cosine theta. I'm going to get rid of that by dividing both sides by negative cosine theta. So here we have mu sub k is a over g minus sine theta divided by negative cosine theta. And so we can plug in the values for acceleration. We can plug in the sine theta, and we get that mu sub k is 0.087. And that is the end of the Chapter 4 homework. Have a great day.